Okay, let's get started. So, in the previous class, we learned about the timing of sequential logic. But I mentioned that usually build we build the system like this. Okay, so you can find the two D flip-flop, and then between these two D flip-flops, so you can find the combinational logic, and then the delay of this combinational logic plus the delay of D flip-flop needs to be lower than the period of this clock signal. So this is very important. And then so also we learned about the timing constraint of deep flip-flop, the setup time and hold time. So you need to understand the meaning of a setup time and hold time, right? This is very important. So setup time means that the input of the deep flip-flop. So the D is the input of the deep flip-flop. This input needs to be stable before the setup time on the rising edge of a clock. Okay, so this is the meaning of a setup time. And then hold time is that, so at the rising edge of the clock, the input signal needs to keep the value. Okay, this is the meaning of a hold time. So when this the system is built, so which means that when we build this the system using deep flip-flops and combinational logic, then uh, we need to keep this setup time and hold time. So which means that so this setup time and hold time needs to be kept. Okay. So if the setup time and hold time is violated, then the system will work unstably. Okay, so we also learned that where is the okay. So also deep flip-flop has the delay, like the propagation delay and contamination delay for the output port. Okay, so actually when we calculate when we analyze the setup time constraint and then hold time constraint in the digital system, this delay also need to be considered. Okay, so and then we learn how to analyze the setup time constraint. Okay, and then we also learned how to analyze hold time constraint. So actually the setup time constraint is caused by maximum delay, the maximum delay of combinational logic and deep flip-flop, right? And then the this hold time constraint is so hold time violation, also hold time constraint is violation is caused by minimum delay, the minimum delay of combinational logic, also the minimum delay of deep flip-flop. Okay, so and then we used this example. So this is a timing analysis example using the, so you can find the combination logic here, and then you can find the deep flip-flops. Okay. So then, as I mentioned, when we check the setup time constraint, then firstly we need to check the longest delay, the critical path of this circuit. Okay, so we can start from the D flip-flop, and then we just find some combination the gate. So it's a critical path. So because in this example, for this path, there are many gates, let's say 3 gates. So we can estimate that for this path is the critical path. The critical path means that it's the longest path, okay? Because there are many large gates. And then when we consider the hold time constraint, then we need to select the minimum delay path, okay? So, and also some student asked the question after the class. So actually, so in the class, in the previous class, I showed that this is the minimum path. Also, this is the minimum path. Okay, because there is only one large gate here. So, and then if the hold time violation is detected, we can avoid this hold time violation by adding buffer, right? So buffer is just a back-to-back inverters. So inverter is also delay. So we can, which means that we can add delays on the minimum delay path. So we can avoid the hold time violation. Okay, this is what we learned in the previous class. Okay. Okay, so now, so it's another some constraint. So now, so we will learn about the clock skew. So what is the skew? So I mentioned that clock signal is the periodic signal, and then this period of this clock signal is fixed, right? So we can find the clock signal is the periodic signal. Then so 1 and 0, these signal values are repeated, and then the clock period. This clock period is fixed. So it is the some definition of clock signal, and then we use this clock signal for the input of D flip-flop. So by using clock signals, we can just control the timing of digital systems. But so actually the timing of the digital system, so timing of the D flip-flop is actually controlled by this edge, the rising edge of clock signal. So which means that the rising edge is replicated with the fixed clock period, right? So this is the ideal clock signal. So I mentioned this is ideal. So which means that in reality, this timing, the timing of this rising edge can be changed. Why? Because this clock signal is also delivered via metal wire. Okay, so you can find the deep flip here. So this is the clock, and then actually in order to deliver this clock signal to deep flip-flop, so we need to use wires. Okay, and then actually the wires have also delay component. Okay, so and then as you can see in this example, the same clock signal is connected to the many deep flip-flops using metal wires. Okay, so it means the delay. So clock signals are delivered to the many deep flip-flops, but because of wire delays, the timing of this clock signal for individual deep flip-flops can be different. Okay, so ideally, these are deep flip-flops, and then there are many deep flip-flops, and then clock signals are connected to every deep flip-flop, right? So ideally, the timing of a rising edge for these deep flip-flops need to be the same. Okay, that is the ideal clock signal, but this timing can be different because of wire delays. Okay, so this is the difference of clock edge timing is called clock skew. Okay, so skew means that some timing of the clock, like real clock, can be some changes. It's a kind of it's called the skew. So when we analyze the timing constraint of the system, we also need to consider clock skew. So that is the real some the changed timing of clock rising edge. Okay, so it's a clock skew. So if you see this slide, so you can find the some definition of the clock skew. So clock doesn't arrive at all registers at the same time. So as I mentioned, because of wire delays, the clocks cannot arrive at all registers at the same time. So ideal clock. So when we assume the ideal clock, the clocks needs to be arrive at all registers at the same time, but it's not possible. This is because I mentioned it's ideal. So the clock skew is defined as the difference between two clock edges. Okay, so that can be the clock timing can be changed. So this is the example. Okay, so you can find the two D flip-flops, and then clock signal is just connected to the two D flip-flops. So it's like the clock 1 and the clock 2. Okay, but because of clock skew, the timing of clock 1 and clock 2 can be different. So this timing difference is defined as the clock skew. So when you analyze the setup time constraint and then hold time constraint, this clock skew needs to be considered. Why? So actually this T skew, so actually we can define this clock skew T skew as the maximum difference between the clock timing. Okay, this clock skew difference as the worst case. So it's the kind of the maximum timing difference between clock edges. Okay, so this is the clock skew. Then how can we consider the clock skew for analyzing setup time constraint or a hold time constraint? So when you analyze the setup time constraint, so we analyze like this. So this is the D flip-flop. Okay, and then clock is connected like here, and then this is the combinational logic, and then here. And then in order to consider analyze the setup time constraint, we compute the maximum delay between these two D flip-flops, right? So what's the maximum delay? So TPCQ, this is the maximum delay of D flip-flop. Like TPCQ plus, and then TPD is a propagation delay of the combination logic. So this is the maximum delay of combination logic. And then this needs to be less than the TC minus T setup. Right, this is the setup time constraint. Okay, setup time constraint of this circuit. Then, if we consider the clock skew, then how can we analyze this circuit? So, what is the clock skew? I mentioned that clock skew is the maximum timing difference between clock edges. So, this is the worst case actually, but we need to consider the worst case when we build a system, right? if we just consider the very optimal case, then this system can be unstable because of the worst scenario. So we need to consider the worst case, right? So and then class Q is the maximum timing difference. So just to think about it. So how can we consider the class Q in this case? So what is the worst case? The worst case is that so TC is reduced because of clock skew. So why? Oh, when the clock arrives at this T flip-flop, the first T flip-flop, then clock is slow, right? And then when the clock signal arrives at this T flip-flop, then clock is fast. Do you understand? If the clock arrives at this T flip-flop slowly, and if clock signal arrives at this T flip-flop quickly, okay, then this is the worst case, right? Because the timing difference between these two T flip-flop is reduced. Do you understand? So when we consider the class Q, then we need to subtract T Q from this time. Do you understand? So just think like this. So we need to consider the worst case. Okay, so class Q is the maximum time difference. So when we consider the worst case for the setup time constraint, then this actual the effective clock period is reduced by clock skew, right? So clock skew is subtracted from the original setup time constraint equation. Okay, so this is the effect. So some effective clock period when we consider the clock skew. So it's the worst case as I mentioned. Okay, so because of clock skew, then the TC clock period is actually reduced, right? And then so this is the delay considering the setup time constraint, right? So when we consider this clock skew, then TPD needs to be less than the okay. So TPD needs to be less than the TC minus TPCQ and then T0 and then T skew. So because of clock skew, then the setup time constraint is also it becomes worse. Okay, it's worse, right? Because the effective clock period is reduced. Okay. Then how can we consider the hold time constraint? So when we consider the hold time constraint, so actually we need to also consider this case. So we also need to consider the worst case, right? So what is the worst case of this hold time constraint? So it's a different, right? What's the worst case when we consider the hold time constraint? So this is slow, right? So clock arrives at this R1 slowly, and then clock arrives at this R2 quickly. Okay, so fast, right? So when you consider the hold time constraint, then this TCCQ and TCD, this is the minimum delay of this path, right? But actually, this is the original equation of the hold time constraint. TCCQ plus TCD needs to be larger than the T hold, right? This is the original equation, but what's the worst case? Oh, this is slow and this is fast. So actually, it is clock skew needs to be added. Okay. So when we consider the clock skew, then this is the changed equation for analyzing hold time constraint, right? So this. So actually, so when we consider the class Q, then we need to consider the worst case, but it looks like the some the worst situation. Okay, so in the setup time, the effective period is reduced by clock skew, and then when we consider the hold time constraint, the effective hold time is increased because of this clock skew. So when we consider this worst case, then we can analyze this setup time or hold time constraint with the clock skew. Okay. So as I mentioned, this is also very important because when we build the system, then we need to consider this setup time constraint and hold time constraint. And then these setup time constraint and hold time constraints are violated. As I mentioned, the system will work incorrectly. Okay, so that's why this timing analysis is actually very critical, very important. So it means, so it can be asked during the final exam, right? Okay. So and then I will briefly explain about the synchronization. So actually we analyze the timing of the system inside of a system. So it means that we just consider some signals like clock signals and then reset signal. It's generated by some in the system, and then also we just handle the signals inside of a system. Then what does that mean? So actually, in reality, we need to consider the signals from outside of the system. Right. So for example, so I use this pen, right? And then I click the screen so using a pen. So this is the outside signal, right? So and then actually we cannot control the timing of this touch. So this because this is just the outside of a system, right? We cannot control. But sometimes our system needs to communicate with these outside signals, right? And then because we cannot control this outside signals, so we need to avoid then how can we avoid the setup time constraint or hold time constraint? So until this point, we learned about the setup time constraint and hold time constraint of our digital system. So I mentioned that we need to control. We need to build a stable system by controlling timing of our digital logic, like a combinational logic, right? So in order to keep the setup time constraint, we need to adjust the delay of our logic gate. Also, in order to keep the hold time constraint, we can add more logic to increase the delay. Okay, we can control the timing of our system, but outside the signal, we cannot control. We cannot control the timing of this outside signal, right? Then how can you avoid? How can you avoid the setup time constraint, the setup time violation, or hold time violation? Actually, it's not possible. Right? We cannot control. We cannot control the timing of our touch and so the timing of outside signal. Okay. So and then problem is that if so this is the aperture time, like setup time and hold time of the deep flip-flop, and then the signal. This is the outside the signal. So it's a signal from the outside of the system, and then this is a synchronous signal, right? We cannot control. Okay, we cannot control this signal with the deep flip-flop. So we don't know the exact timing of this signal, which means the input can be changed during aperture time. Then what will happen? So this is the input from the outside of a system. Then it's sampled by clock signal by in the deep flip-flop. But this signal can be changed during aperture time. What will happen? So systems can be unstable. But what will happen? So if the input signal changes during aperture time, then we cannot estimate the exact value of this signal. Okay, so this input signal, so this asynchronous input signal will be sampled by clock signal, but during the aperture time, if this input signal is sampled during the aperture time, then we don't know the output of this deep flip-flop, like a cube. So if we cannot know if we cannot identify the output signal of the circuit, then the system can be unstable. So this state is called the metastability. So it means the digital signal needs to have zero value, like low voltage level, or high value. It's a value 1. It means the high voltage level. Actually, the digital signal needs to have one of these two states, like 0 or 1. But because of this asynchronous input for the deep flip-flop, the state can be in this unstable state. Okay? Then so this state is called the metastability. It's a metastable state. Okay. So unfortunately, so usually the digital values are in these stable states like 0 or 1, because of asynchronous input, and then unfortunately the states can be located in these unstable states. So usually, to like this like the hill. So if we just drop the ball in the top of the hill, then we can observe that ball can be goes to this side or this side, right? But unfortunately, sometimes if we just drop the ball on the hill, then the ball can stay on the top of the hill. So this is similar to the metastability of the circuit. So because of asynchronous signal input arrived at the D flip-flop during the aperture time, the state of this output signal can be here. It's a metastable state. Then you don't know the exact value of this signal. So this signal can be maybe around the middle of 1 and 0, like this level. Okay, but if the signal levels can like signal levels become like here, like this, then the system can be unstable. So we need to avoid this case, but as I mentioned, it's not possible actually. Right. We cannot control this, and then we need to sample. We need to sample the outside the signal using the flip-flop. Well, how can we control? We cannot control. But we can reduce the probability of metastability. So this is kind of some difficult. So if we use the back-to-back deep flip-flops like this, so this is the input from the outside of the system. It's an asynchronous system, and then as you can see, you can find the back-to-back deep flip-flops. Okay, then this is the output of the back-to-back deep flip-flops. So if we use this back-to-back deep flip-flops, then we can reduce the probability of this metastability, unstable output from the metastability. It is because, so if we read this slide, so you can find some probability function. So actually, the metastability, the probability function of the metastability is like this. You can find the inverse of exponential. So which means that by time, the probability is reduced. So if the input signal changes during the aperture time, the metastability can happen, but at the some time, then it goes to the stable states, right? So this equation explains this probability. So by doing this back-to-back deep flip-flop, then we can just expect that the metastability is resolved during this clock period. Okay, so by doing this, then we can reduce the probability of metastability. Okay, so just to remember that if the input signal for the system is from the outside of the system, and then if this input is asynchronous, then we need to sample this input using back-to-back deep flip-flops. Okay, so this is called the synchronizer. Also, asynchronous input is sampled by back-to-back deep flip-flop. This is called the this circuit. This circuit is called the synchronizer. Okay, so by using synchronizer, we can reduce. We cannot remove this metastability entirely, right? Because it's a kind of probability function, but we can reduce the probability dramatically. As you can see, this is the function of inverse of the exponential function. Okay, so just to remember that when we sample the asynchronous input, asynchronous signals, then we need to use the back-to-back deep flip-flops. Okay. So, okay, so I will close. So this is the end of the timing analysis of the sequential logic. Then we will move on to the next topic is the arithmetic unit. Okay. So now we are going also we will explore about the combinational logic. Okay, combinational logic again. So it's the arithmetic unit. So what is the arithmetic unit? So actually, until this point, we learned about the many different kinds of digital building blocks, such as the multiplexers, decoders, and then some anyway, so multiplexers or decoders, right? But in order to build the complex digital system, we may require different kinds of digital building blocks. So for example, so let's think about the calculator. So which function is required? So in order to build a calculator, we require add function, subtract function, multiply function, and so on, the divide function. So actually it means, so we may need to build the circuits that can perform these arithmetic operations. So I mentioned the addition, subtraction, multiplication, and division in order to implement the calculator. And then these digital blocks that can perform these arithmetic operations are required. For example, let us assume that we want to build a CPU, so computer processor. And then computer processor actually can perform add, subtract, multiply, and so on, right? So actually, we just handle the signals, it's a binary numbers, and then computers actually perform arithmetic or logical operations using binary data, the binary numbers. Okay, so which means that our CPU, our processors actually include many arithmetic units. Okay, so this time, so we learn how to build arithmetic units. So, okay. So what are arithmetic units? So it's a digital block that is used for arithmetic operations. So as I mentioned, so like the adder, subtractor, multiplier, and divider. So these units performs the arithmetic operations. Okay, and then by combining these arithmetic units, we can build ALU and then floating point units and then processing engine of processors. So I believe you can take the computer architecture course in the next semester, right? And then actually processor includes the ALU. So as I mentioned, a CPU or processor needs to perform arithmetic operations defined by instructions, right? So the processor includes these arithmetic units. Also, floating point units. So also the CPU includes the floating point unit for calculating floating point arithmetic operations. Okay. So now, so let's start from the adder. Half adder and full adder. Okay, so this slide shows the example of binary addition, right? So we also learned about the binary addition, right? So we can just perform from the LSB, okay, the least significant bits. Then, so by adding these two digits, two bits, then the carry can be generated, and then this generated carry is added by these two bits, okay, 2-bit data. So this is the arithmetic addition. So our goal is to implement this addition, arithmetic addition, using basic gates. And how? So what is the output? What is the output of this arithmetic unit? So, and then firstly, so we learned that when we define a digital module, then this digital module includes the input, output, function, and then timing. So actually in this class, so we will not consider the timing of this module. So then, firstly, we need to define input signals and output signals, and the input and output signals are defined. Then we can define functional specification using Boolean equation. We can follow the same step here. So in this operation, what are input signals? So these are input signals like 1, 0, 0, 1, and then 0, 1, 0, 1. So input of arithmetic operations are called operands, right? Operands. And then, so these are output signals. Okay, so the result of addition. Then we can define the functional specification. But in this case, the input is 4-bit and then output is also 4-bit signals. So it's complex. Okay, so we can just focus on this operation. Okay, so digit by digit operation. We can just focus on the one digit operation of addition. Then how can we define input and output? What is the input? Input of this addition for this digit is the speed and then the speed, right? So we can define this is A, this is B. Then what are output signals? Right. So by adding these two bits, we can generate the output, and then this output is called the sum. We can observe another output. Right. So by adding these two bits, sum is generated and carry is generated also. Okay. So when we define the addition, the adder, we can define input here, then output is a sum and carry, right? So actually, if we just focus on this digit, we can find the two big input, two inputs, and then two outputs. But if we just focus on this digit, we can find another input. What is this? Another input is the carry from previous digit, right? So actually, in order to implement the addition, then we need to consider the 3-bit inputs, like so carry, then two inputs from the operands, and then sum is generated, and then another carry out. So carry is generated. So we can define two different kinds of adder. It's called the half adder and full adder. So when we explain about this digit, I mentioned that this digit has only two inputs. So we can define this case. So this case is the half adder. The half adder includes the two input A and B. And then what are output signals? Output signals are sum, okay, and carry out. The carry is generated and then the sum is generated. Then, if we just focus on this digit, we can find that, oh, the carry is generated from previous digit, and then we need to consider the addition for this carry, right? So in this case, this adder has the three inputs A, B, and C in. So it's a carry from previous digit, and then also it also generates the C out and sum. So, we define input signals and output signals, and then based on the input and output signals, we can identify the values of output signals like C out and S. What are the values of C out and S? Is it 0, 0? Is it 0, 0, right? 0, 1? What is the sum? Sum is 1. But K is not generated, right? The 0. And that's the same, 1 plus 0, so 0, 1. And then 1, 1. So 1 plus 1 is 1, 0, right? So means the K is generated, but sum is 0. So we can generate the truth table. And then if the truth table is generated, then we can also generate the Boolean equation. Okay, you can identify Boolean equation. It's the same, so you can do this. So this is the answer for the 1-bit adder. So we can define half adder and full adder, and then as I mentioned, full adder has 3 inputs and then 1 sum and 1 carry out. Half adder has 2 inputs and then 1 sum and 1 carry out. And then you can find the Boolean equation. Okay, so usually for sum, so sum is the exclusive OR of a inputs. Okay, so in this, if you see that this Boolean equation for the sum of full adder, you can find that the sum is the A exclusive OR B exclusive OR C in, and then C out is the AB, so or AB is and then so we can use the AB, AC in, and BC in, then which all products are ORed. Okay, so this is C out. So you can find the basic logic gate that builds the sum and carry for the half adder. Okay, and then also you can find the carry sum and carry out for the full adder. Okay, that's it. So actually it's simple. If we just focus on the 1-bit operation of the addition, then we can just build the half adder and then full adder. Okay, but we use multi-bit signals, right? Because we want represent very large number of multiple bits, right? So actually the arithmetic operations are performed for multi-bit data. So which means we need to build the multi-bit adder, right? And how? So like this, so in this example, you can find the multi-bit addition like 1001 plus 0101. Actually, as I mentioned, the input operand in exhibit the multi-bit data. Okay, it includes the multi-bit data. So actually, when we build the adder is represented like this. So A is the multiple, A includes the multiple bits. So P includes the multiple bits. Okay, and then this adder can receive carry in from the previous digit. So this carry in is the 1-bit input, right? And then carry out is also 1-bit output. Then sum is the n-bit output. So this is the definition. So it's a input and output data of this multi-bit adder. Okay. Then we will learn how to build the different type of adders. So it is because addition. The addition is the basic operation. It's a very fundamental operation, right? That's why we learn the addition the first in the not kindergarten, not elementary school. So we first learn about the addition, right? 1 plus 1, 1 plus 2, blah blah blah. Because the addition is the fundamental, is a basic operation, right? And then actually we can build, we can okay, subtraction is the kind of addition, right? Because like a plus minus b like this. And then actually multiplication is also the extension of addition, right? Divide is the same. So addition is the basic operation, and then it's the same for the hardware design. All hardware design. So all other arithmetic units such as the subtractor, multiplier, and divider can be implemented from basic adders. Okay. So we will learn about the different type of adder. So it is because we can build adder like this, the multi-bit adder, but the performance is different. Then what is the performance? So I mentioned, the performance of adder can be different. Then what is the performance? So we learned about the timing, right? What's the performance? Performance is usually proportional to the clock frequency. So, in order to increase the clock frequency, the TC, then we need to reduce the clock period. And how? The minimum clock period is determined by setup constraint, right? Because you can find the TC in the setup constraint, right? The TC needs to be larger than the TPCQ, TPD plus T setup. If we just ignore the plus Q. So actually, this is the fixed value. T setup and PCQ is the fixed value of the T flip-flop. We cannot change. We can change the delay of combinational logic. So it means the delay of combinational logic determines the performance of our system. So that's why we will learn about the different kinds of adder. So you can find the 3 different kinds of adder here. So ripple carry adder, carry required adder, and prefix adders. And then you can also find some descriptions about these adders. Like ripple carry adder is slow. Carry required adders are fast, which means that the delay is low. Prefix adders are faster. So we can, so this slow, faster than this represents the delay of adder circuit, like the TPD, right? So if we want increase the performance of your system, like the CPU or processors, then these processors need to include fast adder. Okay, it is because so that's why we we will learn about the different types of adder, but we will focus on the delay of adder. It is because we learned about the timing of sequential loss. Okay, let's start from the ripple carry adder. This adder is slow. Why? So, let's start from this example. So actually, okay. So we learned how to add the binary numbers, right? It's the kind of elementary school arithmetic. So, but how can we calculate the sum of multi-bit binary numbers? So as I mentioned, we start from the LSB, right? And then so we firstly calculate the sum and carry, and then using this carry, then we calculate the next digit, and then also it's a 1 or it's a carry is a 0, and then calculate this digit, and then blah blah blah. So what can you observe? So you can observe that addition starts from LSB, and then it is propagated to the next digit until the MSB, the leftmost bit. So actually, and then obviously, when we add two numbers, so we just firstly start from the LSB, and then it is propagated to the next bit, next bit, next bit, and then until the MSB. Ripple carrier. So actually, the ripple represents is propagation, the propagation of the wave. So this is called the ripple. So you know the ripple carrying instead, like this normal addition, the carry is propagated from the LSB to the MSB. So that's why this adder is called the ripple carry adder. The ripple carry adder. Carry is propagated from LSB to the MSB. So actually, this is the circuit. This is the circuit of ripple carry adder. How can you observe? What is this? This is the full adder, right? It's a full adder. So A is here, and then sum is here, and then carry out is here, and then carry in is here. And then you can find that carry out of this digit is delivered to the carry in of next digit. You know, it's connected. The carry out port is connected to the carry in port of next digit. Okay, so if we just connect the carry in and carry out of the full adders, so we can implement the ripple carry adder. Okay, but what is the disadvantage? It's slow. Why? So we can simply analyze the critical path is the maximum delay of this ripple carry adder. So what is the maximum delay? So what is the critical path of this ripple carry adder? So what is the critical path when we calculate the adder? So when they perform addition, actually in order to perform addition for the MSB, we need to know the carry in. Carry in for MSB, but in order to know the carry in of this MSB, actually we need to calculate this one. This one. So what is the maximum delay? What is the critical path? Critical path is is carry. Carry is calculated from LSB, and then this carry is propagated and calculated, propagated and calculated, and propagated and calculated. So this carry generation is the critical path of the addition. Right? It's obvious. So when you calculate the when you calculate the addition of the large numbers, the multi-bit, well, like the multi-digit, then actually the last digit, so MSB is the slowest path. Okay, it's the same for the ripple carrier. It's because the ripple carry adder just implements the normal addition. Okay, the carry needs to be generated here, and then this carry is delivered to the next digit, and then using this carry, then it's generated, and then carry is also generated, and then blah, it's propagated. So carry is the critical path of multi-bit addition. Okay, so that's why it's slow. So we can define the maximum delay, the delay of the carry adder like this. So this is the simplified representation, right? So this is the delay of carried out in full adder, and then actually the maximum delay of ripple carry adder, the T on the ripple is equivalent to the n. N is the number of digits, then n multiplied by the delay of carry out in full adder. Okay. So T ripple is the n multiplied by TFA. And then we can observe that the delay of this ripple carry adder is proportional to the number of digits. Okay. So for example, we want to calculate the integer data. Integer data is the 4-byte data. It means 32-bit data. So if we want to implement the integer adder, so in CPU, so we frequently perform the integer addition, right? Then which means that we need to implement the 32-bit adder. If we just implement the 32-bit ripple carry adder, then what's the delay? Delay is the 32 multiplied by TFA. So this is the delay of the carry out of 1-bit full adder. And then as you can see, where is that? Okay. C out of full adder is AB plus AC plus BC. Right? So it includes the 2 input and 3 input OR. So it's not explained. So the ripple carry adder, the delay of ripple carry adder is 32, like 30 for the 32-bit. So 32 multiplied by delay of T and plus T OR. This is 3 OR. Okay. And then is multiplied by 32. So like the n, if the n is the digit of the adder, so n multiplied by T n plus T OR. So this is the delay of ripple carry adder. Then as you can see, the delay is proportional to the number of digits. So it's slow, but when we just consider the number of gates, then ripple carry adder includes the minimum number of gates. So cost is small, the cost is low. It is because it includes the smaller number of basic gates, but problem is that the delay is high. So which means the performance is low. So this is the disadvantage of ripple carry adder. Then we need to implement the test adder. And how? What's the problem? What is the issue? What is the cause of this long delay? It's a slow path of this ripple carry adder. It's carry generation, right? So which means if we can generate carries more quickly, we can increase the performance. Obviously, right? So the researchers proposed carry look-ahead adder. So what is a look-ahead? So like look ahead. So look-ahead means that actually in a normal addition, enough to figure out the carry of a certain digit, then we need to know the carry of the previous digit, also carry of previous digit, and then carry of previous digits, right? So carry is actually generated like this. But lookoid means that, we can just calculate the carry of this digit quickly by using some input data only. Okay, so that's why it's called the carry lookoid. Look ahead. Okay. Then how? So it's a definition of lookoid. Okay, then how can we calculate the carry more quickly, earlier? Okay, let's start from this carry full adder. Okay, and then let's see how the carry is generated. So you can find that the C out is AB plus A C in, and then B C in. And then in this Boolean equation, then we can observe that C out is 1. If A equal 1, B equal 1. So what does that mean? Regardless of C in. So it means this C out is generated by only input signals like A and B, right? Right? And also if we just rewrite this equation, then C out is the AP plus A plus B C in, right? And then, so if we just see this term, then we can find that, if A is 1 and B is 1, then C out is generated. So regardless of this C in. And then if we just focus on this term includes the C in, so it's the carry from previous digit, right? And then in order to make this term 1, we can observe that A plus B needs to be 1, right? So it means if this term is 0, then this C, even though the C is 1, then this term becomes the 0. So C in is just removed. But if this term is 1, then it is equivalent to C in. What does that mean? It means the previous carry, the carry from previous digit is propagated. So actually for this equation, we can just analyze the property. The property of this carry generation equation, like if actually this term does not include the C in, the carry in, but C out is becomes 1 if the AB is AB are both 1s. Okay, so it means that the carry is generated. The carry is generated only using A and B. And then if we just focus on this term, then it includes the C in. So it means that, based on this value, the C in can be propagated. So propagated to C out, or it can be looped. So we can analyze the property, the characteristics of this equation using C in. So firstly, we can start from the generate part and then propagation part of the carry. So as I mentioned, the generate means that the carry out is generated regardless of carry in based on the A and B. So we just define the GI. It's a generation bit of a certain digit as the A and B. And then propagation is the A or B. So as I mentioned, if the A or B is 1, the previous carry is propagated, right? So we can just rewrite this equation like the GI. It's a generation bit, and then propagation bit of propagation bit, and then it's ended with the Ci minus 1 is a previous carry. So we can rewrite this carry generation. So this is the example. So propagated bit is the Pi. Pi is the AI or Bi, and then generated bit is the GI. It's the AI and Bi. So we can calculate this 1, 1, and then 1, 0, 0, 1, 0, and so this is the propagation, and then this is the generation. So by combining this, we can quickly calculate the carry. How? Because the generation is 1, then this is 1. And then, if we just see this 1, then carry is just propagated. But actually, for the first digit, at B, the carry is 0, right? Because there is no carry here. It means that the carry is 0. So actually, in this case, the carry is not carry, because carry is generated, so 0 is just generated. But after this one, the carry is just propagated, so it's 1, 1. Okay? So carry lookoid adder, then we firstly define the generation bit and then propagation bit. Okay, and then by defining this, and then once the previous carry is defined, and then the carry can be propagated or the carry can be just generated. So you can say that, why is this fast? Because the carry can be generated. But once the carry is determined, we can quickly calculate the carry using this property, right? So in this example, we can just know that, oh, carry is just 0. If we just know the previous carry is 0, then by using this propagation and the generation property, we can quickly calculate the carry out of this. Why? Because propagation, oh, the 0, then it's, oh, it's 1, so it's 1 actually. Because it's generated here. So actually, so carry required data is implemented like this. So carry, the block of carry is generated, then it's combined like this. Okay. So I will explain about the carry required data in the next class. Okay. Okay. So I will start here. Any question? See you in the next class.